I'm gonna record to this computer. Sweet.
Test one. One.
Well, I think we'll get the festivities started. Howdy, y'all. I'm James, Cat5UXW. I'm an electrical engineering student here at A&M, and I'm also y'all's senior director of operations for the radio club. And I'm also the guy in charge of the whole, 160 meter and 80 meter antenna project. So we'll be going over today is going to be an introduction to EZNEC, which is, my preferred antenna modeling tool. It's very easy to use. Unfortunately, Windows exclusive. So unless you have experience with the VMs and whatnot, not necessarily with plug and play for your Linux and Mac, unfortunately. So yeah, I think we'll get this show on the road. So in particular, I'm giving you all the tools to design 160 meter and 80 meter antennas. The project in particular is to come up with the best possible design within our, limitations and budget for a transmit antenna and a receive antenna that will work on 160 meters and 80 meters. One of the things I'm going to require with each of the design is going to be modeling on EZNEC, so to see kind of how the thing behaves, right? Kind of do a testing and validation before actually building anything, right? Okay, so the tools we're going to be using are going to be EZNEC. For all y'all with Windows, I hope you already have that installed. I am recording the meeting, good. And then we'll also be using the onlinesmithchart.com, which we'll be using to calculate actually designing matching networks for various impedances and the like. So we'll get right to it. We're going to start by modeling a just two antennas for 40 meters. We're going to start with, in my opinion, the antenna that I have a very tumultuous relationship with, the infamous coil shortened vertical. It is a classic for portable operations. It's you grab a short, as long of a section of wire as you can that's smaller than a quarter wave. You slap a loading coil on the bottom of it and you spread out some radials. So we're going to start by just modeling that antenna. So I'm going to go ahead and stop share, and then we're going to now share to my whole desktop so y'all can see the whole themabobble. Can y'all see my desktop? Cool. Okay. Sweet. So I already have EZNEC up here, but I'm going to go ahead and close all my stuff. I apologize for the particularly busy background here of my desktop. I really need to organize it. So yeah, so if all y'all are here on the EZNEC thing, I'm gonna want y'all to go hit open, just to open up literally a random document. So it should take you to a folder called, window this PC Windows EZNEC.7 docks antenna. Literally just pick one. It does not matter what it is. Actually, I take that back. Choose bydipole1.ez. So once all y'all have that open, can I get a show of hands to make sure that everyone has it open? Cool. Okay. So first things first, we're gonna go ahead and we're gonna actually, yeah, that's fine. So first things first, here is actually the whole EZNEC, thingamabobble. Here is, where you can actually name the antenna. So we'll go ahead and, rename the antenna to y'all will click here on literally the text backyard dipole. So, I'm gonna name it 40 meter vertical antenna modeling. Y'all can name it whatever you like. It's up to y'all. Okay. So have all y'all named your thingamabobble so far? Sweet. Okay. So next thing we're going to set frequency to our frequency of operation. And so say we want to operate, 40 meter voice, we're just going to press 7.2 megahertz. So y'all can go put that in and set that to that. Sources, we'll go over sources in a little bit, but in particular, the way this works is EZNEC is a modeling software that you define segments of wire and then put like sources, aka connecting coax to it, or like adding a load, so like an inductor capacitor sort of something along the antenna wire. So you can have multiple sources in an antenna system to simulate what an array would look like, or you could have, multiple sources for, I don't know, whatever possible thing you could imagine. Maybe you have two antennas that, yeah, it's all just antenna arrays. So we're gonna ignore this sources tab for right now, but we're just gonna kind of leave it, here off on the side. Transmission lines, we're gonna ignore that. Transformers, we're gonna ignore that. I do want y'all to open up the loads menu and then just kind of leave it off to the side. We'll come back to this guy later. The loads is under the sources tab, and so just a little arrow. Okay, so we're gonna ignore transformers, we're gonna ignore L networks, we're gonna go to ground type, and you're gonna hit high accuracy for your ground type. This is gonna simulate what it's like over a conductive plane, similar to like, you know, soil and the like. Um, Ground description, you can calculate what your ground looks like in terms of conductivity, but we're just going to leave it as is. You can go do some more research on your own time to go and figure out actually what the ground conductivity for your area is. So then we're going to go to wire loss. This one's important because EZNEC will allow you to model each segment of wires having its own distinct resistance. what the wire tab is says that any new wire that you make already has an automatic, resistance to it. So say you want to, design like something with this with a stainless steel section of wire. You can model that to see what its performance would be like versus if it was a copper section of wire. So we're gonna go and we're gonna set it just to copper, So any new wire we make is just, nice little copper wire, nothing too fancy. And for units, you can change it to whatever you like, but we're in the United States, so we're going to use feet. Feet just makes life easy. And so yeah. So then we're also going to set plot type from azimuth elevation. We're going to set it to three-dimensional. So this way, whenever we can actually design an antenna, see what it looks like, and then see its 3D radiation pattern, which is pretty handy. You can get some pretty complex patterns with certain stuff. And so we're going to ignore the rest of this for right now. So first things first, we're gonna go click on the wire segment, you know, or the wire tab to kind of start looking at our, excuse me, sorry, start defining the actual lengths of our wire. So do all y'all have your wires tab open? Cool. Can I get a show of hands? Sweet. Okay, so let's go with the classic problem. Let's do, your classic 8 foot tall, mobile whip vertical antenna. This is a classic, it used to be that you could buy a 102-inch stainless steel whip, for 20, $30 at your local CB shop. Local CB shops aren't as much of a thing anymore, but they're still out there out in the wild, and you can still buy them. DX Engineering will sell a 102-inch stainless steel whip for about $30, $40, but it does cost you $20 in shipping. It's, basically, 102 inches worth of steel kind of coiled on itself. Okay, so we're going to start by defining this wire segment as N1 as just being zero point 0.1, feet off the ground. That's saying we're not actually connected to ground, but we're basically right over ground. You can connect stuff to ground with EZNEC. I just recommend not doing it because then you need to kind of look, you would need to read the manual, see exactly how it behaves. It'd be better off just putting your stuff close to ground instead. And since we're using an 8 foot tall whip, we're going to go and what are we going to do? We're going to go and set our wire N2 to X0, Y equals 0, and then Z equals 8.1. So that way, it's just a simple antenna. And if y'all will go click your view antenna tab there, y'all should see something pretty similar to what I've got here. The view antenna tab is going to be on the far left, set of menus under the SWR tab, just a view antenna tab, which will allow you to kind of visualize the thing in 3D. Do all y'all have that open? Cool. All right. So our next step is we're gonna, move the source of our antenna. So right now it looks like we just have an 8 foot long section of wire that has a feed point in the middle of it. But a vertical antenna is fed from the base. So what you're gonna do is you're gonna come here to sources, you're gonna change it from 50% from end one to just 0% from end one. And that way, so we just kind of move the end down here. Okay. Let me know whenever y'all have that done. Do you have that done, Chris? Alana? Sweet. Okay. All right. So it should look like this. Yeah, you all should get an error. It says, source on an open end. EZNEC doesn't like open-ended sources like that. So that just means we're on the right track so far. So next thing, every time you deploy a vertical antenna, it needs to have some radials, right? So we're going to go and we're going to define a new wire, start at 0.1. We're going to set X of, 33 because 33 feet is about a quarter wave on 40 meters. And we're going to hit the Z to be, zero point 0.1. So it's basically just a flat wire along ground. Yeah, that is right. Okay. So then the next thing we're going to do is all right, let me know whenever all y'all have the one ground wire down. Let me know if you're having issues too. Okay, you got it. Do you got it? Set your Z on N2 to be 0.1. We don't want this connected to ground. How are you doing over there? You got it? Okay, let me go see. The way you add new wires in EZNEC is kind of clicking the next available cell and and just fill in the data that you want, and then it'll autofill the rest. Okay, so next thing you're going to do is you're going to go to the Create tab, and you're going to hit Radials. So we're going to make a bunch of radials. So you can copy stuff around. You can have a more complicated radial system. It says first wire in prototype group, last wire in prototype group. Since wire two is our only radial, we're just going to set the first wire being number two and then the last wire being number two. So it's just that one wire. And we'll do, we'll get fancy with it. We'll do six radials. You know, it'll look all, hexagonal like this right here. Let me know whenever all y'all have your radial wires. So if you want to delete a wire, click on the wire tab, click delete, and then and then type in your range of wires that you want to delete. So say I really have beef, with wire, number seven, right? Because maybe say I'm deploying this vertical, up alongside my fence, and I can't have, these two radials. I'm just gonna go and delete, wires two and seven. So let me have y'all also delete wires, two and seven. So our vertical just kind of looks like this. This could look like in the real world as you're putting your vertical up alongside the fence. You can't run radial wires into your neighbor's yard, so you just kind of spread them out all along your backyard the best you can.
So we're deleting 3 and 7?
Yes,
Individually?
yes, because the way that the delete tool works, it deletes a range of wires. So you wouldn't want to delete two through seven because that would delete all the radials.
Mhm.
Okay, so let me know whenever y'all's system looks like this.
You just want to delete
Oh, huh, you can do that? Okay, so apparently you can kind of click on one and delete it like that.
but you can't click on that.
Interesting. All right. Okay. So does everyone have their thing looking like this? We've deleted a couple radial wires. Sweet. Okay, so next thing we're gonna go and we're gonna run an SWR sweep. So we're gonna take a look at how this antenna's its resonance is, across, a certain range of frequencies. We're looking for as close to 50 ohm real resistance with no reactive component on the impedance of this antenna. So we're gonna sweep it from 6.8 megahertz, correct, 6.8 megahertz to 7.6 megahertz. And we're going to do a frequency step of 0.01. So that way we'll get it in about 10 kilohertz, degree of resolution of of resonance at any given point. So let me know whenever you all have all this plugged in correctly. You got it, you got it. Sweet. So then we're going to hit run. So it's going to go and do all your calculations there. So y'all should see something crazy like this, it's just the great big old SWR. But if y'all will remember from your licensing manuals and exams, an antenna at resonance is not going to have an SWR one to one. In this case, it's infinity. So what we're gonna do is we're gonna have a little bit of fun with this, shall we say? So we need to calculate an amount of inductance that will cancel out the reactance. So basically, the reactance is down here. It's that, minus J however many ohms, right? So we need to calculate a value of an inductor that will cancel out all this reactance at a given frequency. You can do it with some math, or we can be smart with it. We can open up a new tab on Chrome, and we can just get out a Smith chart because we just have that tool at our disposal. So if you're right here, onlinesmithchart.com, let me know whenever all y'all are on the website. Cool. So we're going to go set our frequency to, we still want to operate at 7.2 megahertz. So we'll put in 7.2 megahertz here. And then, so what you're going to do next is we're going to go and kind of sweep along here until we find 7.2 megahertz. And we see these particular values right here. So if y'all go back to your SWR plot in EZNEC, and then trace it over to find that one specific value of impedance and reactance at 7.2 megahertz. You just click on it and then you kind of drag along it. So does everyone see a value that is basically, about 20-ish ohms with about a kilo ohm of reactance? Okay, sweet. So we're going to do next, we're going to go back here to our Smith chart, and we're just going to plug that value in right there. So, 21.2 or 14, and then negative 1084. Okay. So y'all should see this here on your Smith chart. So this impedance tells me that the antenna is electrically short at the given frequency, just based on its smaller real resistance, and then or its resistance, and then very very capacitively reactive, which also tells me it's pretty short. So we're just gonna grab a series inductor here. We're gonna set this one to microhenries. I'm gonna full screen this here because it's better if you do it full screen. And we're just gonna add microhenries. Keep increasing value until we find that we've canceled out some of that reactance. Let's see what's simply good value. Not 50, 40, 30, 25, 22, 23. Okay, 23 ohms seems about reasonable. So now that we have this vague idea of 23 microhenries, we're gonna get out of that and we're gonna go to our loads tab. So your loads tab here, we're gonna add a load to wire one. So the load is we're adding a bit of inductance along the antenna wire. And so we'll do it 0% from N1, so it's at the feed point. And then we'll click other and we'll hit change load type. We're gonna want to press the RLC so we can express our load in terms of capacitive or capacitance, inductance, and reactance. So you're going to go to your loads tab, or one more time, you're going to go to your loads tab, you're going to hit other, change load type, click RLC, and then your thing should look like this. Do all y'all have that?
Here's a program.
Let's just leave that series. Do you have that? Yeah. Do you have it?
I do not. Before going to other.
Oh yeah, I'll go over that again. So what you're gonna do is you're gonna press wire segment number one. We're just type in wire segment number one, apply the load 0% from the end. So basically what this looks like construction wise, you take your center pin of the coax or right from your transmission line and stick an inductor right on it. And then we're just gonna put in 23 microhenries. Let me know when everyone has that. You're going to want to type here in your L tab 23 microhenries.
I don't understand why.
Basically, what the Smith chart is showing us here is that we have some amount of reactance, right? And we need to cancel it out with the value of inductance at a given frequency. So each of value of microhenry. 1 microhenry has a different inductance at a different frequency, right? So at high frequencies, so let's change this frequency span to 14 megahertz. That actually go straight to 50 megahertz. That 1,000 ohms worth of inductive reactance is now worth 7,000 ohms. And if we go down to let's say just 1 megahertz, our 1,000 ohms worth of reactance is now about 150 ohms, right? So what you need to do is you need to find the right value of inductor for your given frequency. Okay. Right. So that's what we're doing. Go ahead.
So on the loads, it says unit is 0.
Yes, microhenries.
Isn't that one?
Yes.
Okay.
That is microhenry.
Oh.
Okay. Do all y'all's things look like this so far? Is yours ready to go? Okay, cool. Well, we're gonna do some tuning on our side. So once y'all are ready, y'all are gonna hit the SWR button and just run the sweep again. Okay, cool. So y'all should see that, once that thing is ready, we are starting to resonate this antenna. Most radios will put out, full power at, a, 2 to 1, and under impedance, sometimes under a 3 to 1. So right now we see that our, system is resonating about, 7.33 megahertz, right? And so there's one thing with, the limitations of actual of modeling, and the way that this model works on wire segments is that it's not always the most accurate, right? Once you actually deploy in the environment, you can't account for everything. So once you deploy in the environment, you're going to find you have to, change your value of inductance a little bit just to kind of, I guess match it the best it possibly could be, right? But I mean, this is pretty good, but we'll treat it as if, the simulation was an actuality, right? So since if your resonant frequency is higher than you'd like it to be and you're adding an inductor, we need to add more inductance to resonate it lower. So if y'all will go back to your loads tab, and we're going to change it from 23 microhenries to 24 microhenries. Let me know whenever y'all have it now at 24 microhenries. You got it, you got it, you got it, sweet. And we're just gonna run that SWR sweep again. Okay, so now our resonant frequency just so happens to be perfectly the 7.2 megahertz. So, this antenna is resonant. If you have most, say if this was the actual thing, if we had, your radio that has a 2 to 1 SWR or 3 to 1 SWR tuner, this thing would tune it, right up, right? So the other cool thing you notice here is that, we change our value of inductance a little bit and we're able to change the resonating frequency. So if we were to do a coil loaded vertical, you'd want to have a way where you can kind of, you know, I guess add or remove inductance from the system. Let me show you all another interesting way we can, resonate I guess, resonate the system. So say we have a fixed value of inductance, right? This, 20, yeah, so let's say this 24 megahertz inductance is, non-negotiable, right? Our manufacturer boss said you must have, this 24, um, microhenry thing. What we can do is we can shorten the length of the whip. So if we shorten our antenna, that raises its operating frequency. So we go here, we're going to change our height of our antenna from, you know, 8.1 or 8.1 feet to let's do 7.9 feet. And once you have that, run your SWR sweep again. And you'll find that we've raised the resonant frequency by about, 80 kilohertz, right? So, there's an art with coil shortened verticals where you want to have, more inductance over less, or it really depends on what you're able to fit into your system. Okay, so say this is our final antenna. Say we changed our mind and we want to operate on 7 dot, 2 megahertz. Actually, yeah, we'll stick with that. So if we want to then simulate, see what this antenna's radiation pattern and gain is like, you are going to go back here to the frequency tab, and you're going to hit, from 7.2 to, 7.27. There's another interesting tool here with the rescale button, so that if you design like a dipole that's, halfway perfectly resonant on, 14 megahertz, and you want to say, scale it for, 28 megahertz, you can click the rescale button and it will change all your dimensions accordingly. So it's pretty cool. Okay, yeah. So you shouldn't have to run the SWR sweep again because what the frequency here changes is kind of some of the other stuff. So I want y'all to click far field plot. So y'all should see now that we have, you know, um, I guess what the far field of our antenna looks like. So you can see that, well, if we go back here and change from plot type from elevation to 3D, I think I must have forgotten to do that. We can see kind of what our radiation pattern looks like in 3 dimensions. And if we compare our view antenna to our radiation pattern, every time we move this guy will move accordingly. So with a system like this, it looks like that whatever direction all the radials are in with this coil short vertical, it seems to have a good bit of appreciable gain. So if we go to show 2D plot, you can get azimuth and elevation slices for every given frequency of the 3D model. So we can see that right here at about, wow, this is not the world's greatest antenna. I will say, coil shortened verticals tend to be very, they tend to lose a lot of power because they have tend to have a low resistance in comparison to, other kinds of antennas. Um, I guess how to put it, they have a lower radiation resistance because they're electrically smaller compared to like, proper, quarter or full or half wavelength, right? And so if you look at, you have some amount of radiation resistance in your system, and you have some amount of ohmic resistance, which is, resistance in wires, resistance in connections. And if you look at a ratio of, ohmic resistance to radiation resistance, then you get like kind of an efficiency of the antenna, right? So if we have, you know, let's say there's 100 ohms of impedance in the system. 90 of those ohms are, ohms of radiation resistance, and 10 of those are ohmic resistance. Well, that's, nice, 90% efficiency for our system. But say that we have, 10 ohms of resistance in our system, and then, or 10 ohms of radiation resistance in our system, and then 5 ohms of, uh, ohmic resistance, that is two-thirds of your power being transmitted, but that is additional third of your power that's being given off as heat. So one thing you're going to want to consider when you're designing antennas is if it's not terribly efficient, you may want to not run full power into it because you may just be, building a dummy load where you give off all your power as heat. And I don't know about y'all, but melting wires and melting capacitors and melting insulation, not the best time known to man. So yeah, so the other cool thing about having our elevation slices, we can kind of see a front to back ratio. So the gain in one direction versus the gain in the other. I don't 100% know why this system has this low of gain. That might actually be what it looks like. But there's another tool you can use where if you go back to wires, you can do auto seg and conservative, and it'll kind of mess around with the segment of wires. I don't think it's going to behave exactly the same. Sometimes you don't want to always hit, um, auto conserve because whenever you kind of move around your segments of wires, that position of the load and the feed moves around. So if you look at it here, it looks like we're feeding the vertical, from oh shoot, give me a sec. It looks like we're feeding the vertical from the center and loading it at the center. And if you look at it, our, the impedance of our system is way, way, way off, right? So, if you want to undo a change, you go here and just do your Control Z. That'll fix everything right up, and our antenna will start behaving, the way we want it to. So yeah. So okay, how are we feeling after modeling a coil shortened vertical antenna, kind of placing radials, removing some radials, adding a load, modeling it, see what its SWR is like, and its radiation patterns like. How are we feeling? Thumbs up, thumbs down, somewhere in the middle. Um, why not quite thumbs up? What do you got?
Or I understand it now. I just wasn't fully
I got you. Okay, okay, okay. Well, speak up if next time you're stuck. Okay, cool. So we yes, that is a core shortened antenna, but it's two kinds of a core shortened antenna. What this might be is there's an inductor coil at the base, and they're using a series LC circuit, which basically you can think of it as like an auto tap, right? So at a certain frequency of 70 centimeters on this handheld, there's an inductor and a capacitor here that kind of is connected to one turn of the inductor that loads this thing. And at the resonant frequency, all the RF passes through this little series inductor capacitor and, just makes and kind of electrically shortens the coil by shorting out a bunch of turns. So that's how antennas like these work. They're not even remotely efficient, but they work. You just turn it on and it works well, right? Okay, cool. So if y'all, as I mentioned previously, not only are we modeling a coil shortened vertical, we're now going to model my favorite kind of antenna, the random wire antenna. And it is almost exactly what it sounds like. It is, you know, a random length of wire that, is an antenna. So, I'd like, we're going to go back here to wires. We're going to, delete all of our wires except for wire one. So we kind of, start from scratch, and we're going to delete one of our loads here. Um, Let me know whenever y'all have deleted, your inductive load and, your wires, I guess, 2 through 5. Yes, we're going to keep the source. All right, are we all at the step here? Cool. Okay, I'm also gonna go and shrink this down. Okay, so a very popular, kind of an, I guess, random wire, way to do a random wire is you get like a 33-foot mass, you run wire up it, and then you kind of run it down at an angle. So we're literally just gonna model that. So we're gonna start by, we're gonna elevate our feed point a little bit, right? So we're gonna go from Z of 1 or Z of 0.1 to Z of 1, and then we're gonna go up, to about 30 feet. So we now have a, 30, 3 foot, or I guess 29-foot tall, vertical radiating element. Okay, let me know whenever y'all have your wire segment defined. You good? Chris, you good?
Yeah. You just what's the last thing you just rename?
I did rename the thing. If y'all want, y'all can go and rename the antenna. Actually, I'll encourage y'all go rename it to whatever you'd like. Random wire, random wire experiment, whatever floats your boat.
Did you save that?
We didn't. We'll go through saving on the next one. That's fine. You can rewatch the video if need be. Okay, cool. So, we have our nice, little 30-foot vertical and say, we put our mast out in our backyard, and we have, let's say, another tree that's, 60 feet away. That's also, 30 foot tall. So we're going to go define a wire two, which is going to start at, one end be at, 30 feet. And we're going to go across, about 60 feet and we'll go, another 30 feet. So we should have an inverted L that looks like this. Does all of y'all's antenna look like this, wonky L shape? Give me show hands. Okay, you got it. Okay, cool. And Chris, where are you?
Right now I'm on
Okay, do you have your first wire defined as going from 1 foot to 30 foot, and then another one going from like 30 foot to like, 60 feet over, still at the same 30 feet of
Yeah.
elevation? Does your thing, that does not quite look like an inverted L. Yeah.
the 30.
Yeah, so it should go from Z of 30 feet over, 60 feet in the X direction, and then a Z of 30 feet. So, say you got two poles or two trees in your backyard, you just run a wire up and you run it, across. Cool. All right. So, every antenna, needs a counterpoise. So we're just going to go, we're going to create, well, actually, no, we're going to go start at, make a new wire number 3, start at Z1, and we're just going to go back, I don't know, negative 17 feet, and we'll go to height of 0.1. So we have a nice little mini radial here that's, kind of, I don't know, maybe serving as kind of the other half of our antenna. Okay, let me know when all of y'all are there. You got it. It might help if you can um, drag down this guy right here. That way you can access make it simple. So then it's going to go from a Z of 1 foot to X of negative 17 to Z of 0.1 foot or feet.
0.1.
Yeah. So basically right over the ground. Basically what we're doing is we're just kind of sloping this wire to the ground, right? Okay, cool. So we have a, just a funny looking L. So what we're going to do is we're going to set our frequency to our highest operating frequency. And so we're going to say we're going to operate this guy on 28 megahertz, right? So we should see an error here. It's saying, hey, our wire segments are too long. Once wire segments of a certain length for it to be, modeled accurately. It's better to have more wire segments than to have less wire segments. But obviously there's, a bit of an art there. But that's fine. So we'll just go and we'll hit that wire button. We'll hit auto seg conservative. And that way, it likes our antenna and its number of segments on, 10 meters. Let me know whenever y'all have your wires auto segged or auto segged. You got it?
Yeah.
You got it? You got it? Sweet. Okay, so then we're going to run an SWR sweep, and we're going to cover the entire HF frequency. We're going to go from 1.7 megahertz. Well, we'll do 1.8. 1.8 megahertz all the way up to, 30 megahertz, and we'll do it in zero point 0.1, frequency steps. So every 100 kilohertz, we'll see what the impedance of the antenna is like.
1.8 to where?
1.8 to 30 megahertz in steps of 0.1 megahertz. And this one will take a while. There's kind of an art to be had with, sweeping a large number of frequencies. It always helps if you have your computer plugged in, because sometimes this thing will run very slowly given the ability to do so. So once your thing is done, you should see a plot that looks like this. Like this antenna already has a number of resonances. So, there's kind of this neat thing of you have your voltage and current distributions, going across an antenna. And, sometimes it finds some resonant points, sometimes it doesn't, right? So you're seeing this kind of, funny looking pattern. We already have some natural resonance in the system, right? So we're gonna go, okay. So let's tune this antenna for, let's see. Yeah, let's make this simple. We're gonna tune this antenna for um let me think. What seems like a good impedance here? Sure, let's tune this antenna for 7.1 megahertz. So let's change our frequency up here to 7.1. Actually, we'll do 7.2. Cool. Okay, so let me know whenever, y'all have your values here handy. Does everyone got their values here? Sweet. So what we're gonna do now is I'm gonna introduce you all to more of the Smith chart for, like actual impedance matching. So there's a bunch of different sections on the Smith chart. If you go above like the top half of the Smith chart, that means we have inductive reactance. So inductive reactance is canceled, with capacitance. If we're below it, we cancel it out with inductance, right? So then, and also if you move, forwards and to the right, you have a higher impedance. To the left, you have a lower impedance, right? So if our center point here is 50 ohms, all the way to the right over here, this might be, I don't know, 150 ohms, and all the way over here might be, oh, I don't know, like 25 ohms or 20 ohms, right? So what we're going to do now is, take a look at this chart here. This is handy. So we're going to be using what's called an L network. So it's a very simple combination of an inductor and a capacitor, to, match our antenna. So certain kinds of L networks work better than others. So what we're going to do is we're going to go over back to our Smith chart, plot our existing impedance at our desired frequency, and then come back and take a look at this table to see, hey, what kind of, matching network would be best for this sort of application. So if we go back, if we, I'm gonna split screen this here. So I see at our frequency of 7.2 megahertz, we have a impedance of 104.3 ohms, and then an inductive or capacitive reactance of 646.8 ohms. Okay. So if we look at that here, well, actually it's negative. That's my bad. So we look at it down here, we have our, at this frequency, our impedance kind of all the way over, to the right side. So if we go back here and take a look at our, thingamabobble, highly technical term, by the way, we can see that the forms of impedance matching that are probably going to work best are going to be our series capacitor and then shunt inductor, or shunt capacitor and series inductor. So the difference between shunt is basically, if you have your center pin of the coax and then the outside of the coax, shunt would just be connecting the center pin to the outside of the coax at that given point, right? And series is just, keeping it along with, the, center pin of the coax. So looks like right here, that the series capacitance shunt inductance works pretty well for application. It looks like our shunt capacitance series inductance would work somewhat well, but we'll just, do the series capacitance shunt inductance. So what that's going to look like is, well, actually, if we go back here, you can see that the left side is kind of coming in from the radio, and then the right side is kind of going out to the antenna, if I'm not mistaken. And if I am mistaken, we'll find out really quickly. So we're gonna go and add here. We're gonna add a shorted inductor and then a series capacitor. It does. Yeah. So I'll do an example of that once we have this, sorted out. So we're going to change this guy to, microhenries, and so we're also going to set this 60 picofarads. There's a number of common capacitors that'll do about 60 picofarads, about like 160 to 300 picofarads. It's good to know whenever you're designing matching networks that, sometimes um, we have a little bit, too many, component values and whatnot, right? If you're looking for a 1 picofarad capacitance in your system, that's crazy difficult to achieve. So, mess around with your component values till you have stuff, on hand. So we're gonna just kind of play around with, this initial value of inductance. So it looks like as we add inductance, we kind of start closing in here. And so you can add a constant VSWR circle down here of 2 to 1. So if we can get this thing under 2 to 1, our system's going to be working, as intended. Any little mismatch, can be handled by our radio. So it looks like, between the 3 microhenries and the, 4 microhenries, we were on to something there. So, or maybe not. Let's see. 6 picofarads, about 5 microhenries. Oh, actually, no, we'll keep adding more inductance. So 6 microhenries, 5.5. So just this simple value of 5.5 microhenries and 60 picofarads, boom, we're already within our 2 to 1 circle. So if you were to build a matching network to these specifications and hook it up there, you may have to tweak the values a little bit, but this will already be at resonance, right? So yeah, so shunt inductor of 5.5 microhenries, and then series capacitor of 60 picofarads. But say, 60 picofarads is at the bottom of our, the absolute minimum of our capacitor, right? And so say we want to design our system to be able to tune it a little bit. So we're going to increase our capacitance, let's say 100 picofarad, actually, maybe not 100. No? Okay, maybe not 100. Let's see. Maybe. So SWR circle is down here in settings and feature, and there's a tab called constant VSWR circles. So then you just hit the plus. Yep. So yeah, we'll go 80 picofarads, and we'll just increase this inductance to do 1 microhenry, 2 microhenry, 3 microhenry, 4 microhenry, 5 microhenry, 4.5 microhenry, 4.75 microhenry, 4.25 microhenry. It's really a little bit, of an art of, kind of matching around the Smith chart. I mean, you can always calculate this stuff like by hand. But I always like, picking values and just kind of messing it around. Because in the field, when you're deploying these antennas around your house, you're not going to have, a perfect, calculator always. You may only have some amount of inductance and some amount of capacitance to go ahead and match your system, right? So, okay, cool. So we have this thing resonant, at our, desired frequency, basically resonance, here at our, 2 to 1 SWR 7.2 megahertz. So what we're going to do is we're going to then, move our, I guess, recalculate the system at a different frequency. So we're going to go up to 7.3 megahertz. So, ooh, I made a mistake. I made a tiny little mistake. I should have mentioned that our frequency of operation was, 7.2. I actually left it at, 7. But, we'll use this as an example. Say we have our system already tuned at this given impedance at 7 megahertz. We'll go to, 7.3. So you already noticed that, changing our frequency by 300 kilohertz has already moved us significantly along the Smith chart. Our component values are, we used to still be in here, but now not anymore. So that's fine. So we're going to go back here. We're going to get at our new value or measurement of impedance. We have an impedance of 100. What was it? 101.8 ohms minus 600 minus 601.1 ohms. So, okay, cool. It looks like, we're just going to maybe need to add a little bit of inductance. So let's do 5. Yep. So just decreasing our inductance by, 0.5 microhenries. We already just re-resonated the system. But, say only your capacitor is really variable. Maybe you just need to change that value a little bit. The neat thing about this this chunk of software is that you can kind of get some tolerance percentages. So you can actually calculate more of a particular value. The closer that this guy is to the center, the more efficient your antenna is going to be. So you can kind of start to get a feel. Even just changing a little bit of your component value is going to change your resonance significantly. So keep that in mind whenever you're out there in the field operating. Our environment may be significantly different, such that our impedance may be higher, may be lower, may have more reactance. So, designing a network that can handle a wide variety of situations, might be useful. Okay, so how would you actually build this? There's a wide variety of different ways to do this. The biggest, hardest part is the variable capacitor. The variable inductor isn't that hard. You literally just get a coil of wire and then just get an alligator clip and just start shorting out turns. I mean, it's really that simple. You can find a bunch of old capacitors and old ham equipment. You may just have to take it out. But I think I've given you all a decent enough introduction to kind of, the world of antenna modeling. Like the stuff that we just did is the stuff I do a lot of. It's, let me pick a certain geometry of an antenna. Let me measure its impedance across a whole bunch of different frequencies, and then see what I need to do for matching stuff. I'll leave y'all with one neat thing. So how many of y'all here have heard of balun transformers? Like a 4-to-1 balun, like a 1-to-1, 2-to-1, you know? Okay, that's general class stuff, but that's fine. You can actually model that pretty quickly. So if we go here to our alt SWR and set it from 75 ohms, let's say we're using a 4-to-1 balun. So, step up our 50 ohms to 200 ohms, there's 200 ohms right there. And if we go back here to our, you know, SWR chart, you actually don't need to rerun it whenever you change the reference impedance. You just got to click this button. So, we see that our antenna seems to be a little bit more resonant as we go up to 200 ohms than 50 ohms. You mess around with this, you'll find that there's certain, relative impedances that are really good for a wide variety of ranges versus some that really, really, really suck. And so, yeah. So, say you want to repeat the process, say we look at us here, that same 7.2 megahertz, if we change our reference impedance on our Smith chart here to 200 ohms, see that our, calculations have changed somewhat. So, we just need to vary our values a little bit. But I think that is all that I've got for you folks. Do y'all have any questions, comments, concerns, insults, remarks about the weather, et cetera, et cetera?
So this software is mainly used for wire antennas,
Mhm.
like you would into a helical.
You can model a helical on this thing. It's not the best, but you totally can. I will do one really quickly. So we're gonna go to wires here. We're gonna delete a bunch of wires. Y'all don't have to follow along with this. So we're just gonna have 0 to 1. So we're gonna create a thing called a helix. So the helix allows you to make, that helical that you're looking for. You have all the different, inputs and outputs. So we're gonna do like say a 5-turn helix with a diameter of 2 feet, and we want it to end, we're gonna start at, let's see, start at, foot. So not the world's greatest helix. You may need to add a couple more segments per wire. So if we go back here to create helix, number of, thingamabobbles per turn. Let's just set this to, oh golly, I don't know, let's just say 10. Okay, not quite, but mess around with the settings. A lot of this, I'm not going to go too much into this, but there's a lot of different settings and different things you can mess around with for antennas like this. So yeah, no, this is a very powerful set of tools. Knowledge of the Smith chart along with, knowledge of being able to calculate what an antenna's impedance or a whole bunch of different frequencies will allow you to make a lot of different antennas. So, you can use this. I don't think there's an actual frequency limit to this software. You can model it for whatever frequency, but at a certain point you can't really get, 100 picofarad capacitor, for I don't know, or I guess what, 10 to the negative 12, picofarads capacitor for some microwave band. But you can do there's a type of antenna called the biquad antenna. that is used a lot on 1296, which is literally just, two two squares kind of just connected to each other side by side, and you can model that here in EZNEC. Just gotta calculate where each of the different wire segments would be. One last, I'll leave you all with just two more things now, come to think of it. You can change your ground type from, real to perfect, which would be, perfect conducting plane or free space. So if you want to see what antenna just kind of behaves like kind of out there in the wild, that's that would be your free space. So if you're designing like a Yagi antenna, that's high above ground, for like a 2 meters or, 1.2 gigahertz, you would start with, a free space and then maybe look at modeling it above ground to see kind of how it would behave. The other thing too is you can also change your wire diameter here. So you can use like the American wire gauge. So say if only you have is AWG 22 wire, you just put number 22. Say all you have is 10 gauge wire, number 10. So yeah, that's all I've got. Y'all got anything?
So this would have been useful for winter weather.
This would have been useful for stuff like winter field day. So, say if we were to build an antenna or want to see how an antenna would behave. So say you have a dipole you're a big fan of. You can model it, see what it would behave like, and then, see what in actuality it compares. So one of the things you can do, there's a number of antennas called, trap dipoles where you have like a, capacitor and inductor in parallel. You can go and hit load type. Let me see. Load. Oh, geez, I don't know which one. Yeah, here it is. So you can do series, parallel, and trap. So you have all your various settings here. So if you have, 100 picofarad capacitor, in parallel with like a 10, microhenry inductor, and, you calculate it has a series resistance of like 1 ohm, you can model all that in here and it'll, give you an estimation, see what it's like. Any other questions? There are no stupid questions, only stupid answers. Now I'm the only one who can give stupid answers. So, ask away. All right. Hearing nothing, I think that's the end of our workshop here. Solid, 55 minutes worth of, antenna training and modeling. But, this is a very powerful tool, and I encourage y'all to mess around with it. If you want to build an antenna, model it first, see what it's like, and, then build it. So, yeah. All right. Well, I want to thank y'all for turning up, and that's the end of that.
Good job. Thanks a lot.
Thanks, Tom.
You bet.
All right. I will end the meeting here.